Hey, how's it going, everybody? I'm turning on some music so I don't go crazy sitting by myself. I'm gonna skip the ad. Cool. So, we're on day 2 of Exam 2 material. Last time we talked about sequences. Today we talk about series. I made a big deal about it last time. I'll say it again. Series and sequence are not the same word. They are completely different words in math, and you got to keep them straight. Like, this is a main thing that people get dinged a bunch of points on for this upcoming exam, is using the wrong word or not being clear what they're talking about when they're trying to talk. A sequence is a list. When I write 1, 1/2, 1/3, 1/4, ... That's a sequence. A series is a sum. If I write 1 plus 1/2 plus 1/3 plus 1/4 plus ... that's a series. The main way we're going to write that, you saw sigma notation at least a little bit in Cal 1. We're going to express a series with sigma notation. The expression sigma n equals 1 to infinity an indicates a series. If you got through Cal 1 without learning what the sigma notation means, the sigma means take all these things, which ones? The ones indicated by this index set, and add them up. The sigma is a capital Greek S. The S is for sum. It's probably S is for the German word for sum. This is an infinite series, because there are infinitely many terms. Not because they add up to infinity, although often they will, sometimes they won't. Since there are infinitely many terms. In real life, basically whenever someone says the word series, they mean an infinite series. Because if there's only finitely many, you think about that differently. Like, there's a lot of questions about an infinite series. Are you actually able to add up infinitely many numbers? The things that are interesting about a series are generally only interesting if there are infinitely many terms. So when we have finitely many terms added, we'll probably just call that a sum, although the word series technically does apply there. We say that the series converges when the sequence of its partial terms converges. The sequence of its partial sums converges. We defined what it means for a sequence to converge last time, so that word is well defined. What's a partial sum? A partial sum is add up part of the series, some finite part. So, like, for example, if I'm consider the series sum from k equals 1 to infinity of ak. We're going to sometimes use k and sometimes use n as our indexing variable on a series. The difference doesn't mean much, but it's nice to have a second one so that when you're fixing n for a second, you can do something else. Don't stress too much over the switch between the k and the n. I guess you've done integrals with respect to lots of variables. You're already not thrown by the variable. S1 is defined to be A1 for this. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. And in general, Sn is the sum from k equals 1 to n of ak. Is the sum of add up the first n terms. These are finitely many things added. You're definitely allowed to add finitely many things. In this situation, if the limit as n goes to infinity of Sn exists, Sn is a sequence, exists and say it's L, then we say the sum from n equals 1 to infinity of Sn is L, and it exists. We tend to think of n as the main letter. I'm using an n here because I'm talking about the full series. I'm using k here because I want to say what do I get when I add up the first n terms. Here's one of these contexts where I need both the n and the k. Sn is add up the first n terms. I need a new indexing letter to say what is it that's going from 1 to n, so I grab k to be my temporary sub indexing letter. So that's what a series is. And the series exists, the series converges when the sequence of its partial sums converges. Let's try an example where they converge. Let's talk about a geometric series. Should I talk about Zeno's paradox? Is that in my lecture notes? Let me just talk about this. There was a Greek dude named Zeno. I think he was Greek. He had a bunch of paradoxes. It's cool to come up with paradoxes if your name already starts with X. You got 2 cool X words going on named after you. And it starts and ends like a Xerox. The word Xerox is in there. Zeno's paradox is this. To move from point A to point B, you first have to get halfway there. And then you have to get halfway from the halfway point to there. And then you have to get from that halfway from that point to there. And so on. So there's infinitely many things must happen. And therefore, movement is impossible. I feel like what he's really observing is that in an interval from somewhere to somewhere, there are infinitely many points. He probably didn't know what a fraction was. So the idea of having infinitely many numbers in a finite interval probably bothered him. And that's a difficult thing to come up with. Like, it's really hard to imagine how hard it is to think about things when you're missing some of the basic vocabulary that we have today. The fact that there are numbers between 0 and 1 is easier for us to understand, and that there are infinitely many, it doesn't particularly bother us. So the fact that we have to pass through infinitely many points from here to there isn't that weird. But in particular, it is a little bit even more weird that to get from 0 to 1, you're going to have to go through, this has a distance of 1/2, and this has a distance of 1/4, and this has a distance of 1/8, and this has a distance of 1/16. So each of these is an interval, and we need to stack all of those infinitely many intervals on top of each other to end up with the interval from 0 to 1. This suggests to us an infinite series that converges. Let's consider that infinite series. Let's consider the sum from n equals 1 to infinity of, what's a formula for the term 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... This is 1 over 2 to the 1, this is 1 over 2 to the 2, this is 1 over 2 to the 3. If n is going from 1 to infinity, the formula for the nth term is 1 over 2 to the n. It looks like it should be 1. Is it? So this is our chance to use the definition of what it means to take the limit of a series. Like, This whole thing isn't a proof because this doesn't get to what the definition of adding up a series is. The definition of to add up a series is we need to consider the sequence of partial terms and find some way to prove that that converges to 1. So let's consider the sequence of partial terms. Let Sn be the sum from k equals 1 to n of 1 over 2 to the n. We want to show that this sequence has a limit and that the limit is 1. This sequence is hard to mess with because it's got this sigma in it. What we'd really like to do is come up with a formula for what do you get when you add up the first n terms of this geometric series. When you add up the first n terms, you're getting 1/2 plus 1/2 squared plus 1/2 cubed plus ... plus 1 over 2 to the n. This is what Sn is, right? Here's a trick. To understand, like, the geometric series has this nice self-similarity that makes it pretty easy to deal with. The thing I'm going to consider is, what's 1/2 of Sn? 1/2 of Sn is 1/2 squared plus 1/2 cubed. Multiply that by a half, you get a half squared. Multiply that by a half, you get a half cubed. The next one times a half will be 1/2 to the 4th plus ... Plus, I'm going to go back a couple terms. When you're doing these ... it's good to not end on the last term. Let me squeeze in a 1 over 2 to the n minus 1 in it. It'll make the pattern more obvious if I do that. This one, when I multiply it by 1/2, will 2 to the n minus 1 plus 1 is 1 over 2 to the n. The next one will be 1 over 2 to the n plus 1. We're now in a place kind of like what you do when you have a system of equations and you add the two equations together and find that... Oh, hey, let me double check that my stream is live. I don't want to sit here and lecture for an hour to find out that nothing got recorded. Me. I'm live! Can I hear me? It's got my headphones hooked up to it. Double check that my stream is live. I don't want to sit here and lecture for an hour. It was live! Hooray. These two things are almost the same, right? What I want to do is subtract these two terms. Also, be suspicious. I have used this ... symbol here. You should be suspicious when people use a ... I will come back in a second and show how I could have done this without a ... because you want to be capable of doing that. Although in a situation like this where you're trying to understand what's going on, this one will be easier. You'll get more learning out of staring at this version. Let's talk about Sn minus 1/2 Sn. That's going to be this minus this. 1/2 plus 1/2 squared plus 1/2 cubed plus ... plus 1 over 2 to the n minus 1 plus 1 over 2 to the n minus 1/2 squared minus 1/2 cubed minus 1 over 2 to the 4 minus ... minus 1 over 2 to the n minus 1 over 2 to the n plus 1. And I get a bunch of terms to cancel. That cancels. And that cancels. And this is going to cancel with a term right there that I didn't write. And this is going to cancel with a term right there that I didn't write. And this will cancel with this. And the first term of the top and the last term of the bottom don't cancel. And I get 1/2 minus 1 over 2 to the n plus 1. So 1/2 Sn, 1 Sn minus half Sn makes half Sn, equals 1/2 minus 1 over 2 to the n plus 1. Double both sides, I get Sn is 1 minus 1 over 2 to the n, and now I can talk about the limit. The limit as n goes to infinity of 1 minus 1 over 2 to the n is 1 minus 1 over infinity is 1 minus 0 is 1. So yes, the limit is 1. So the series sum n equals 1 to infinity 1 over 2 to the n does equal 1. Check. We did it! To show that a sequence converges to a number, you're showing that the limit of its partial sums converges to that number. We're not often going to go through all the way down to the definition of the limit of the partial sums, but that's always going on behind the scenes. How could I have done that without using a dot dot dot? This is worth thinking about. I would write that Sn is the sum from k equals 1 to n of 1/2 to the k. I would write that 1/2 of Sn is 1/2 of the sum from k equals 1 to n 1/2 to the k. I'm allowed to distribute the 1/2 in. That's the sum from k equals 1 to n of 1/2 to the k plus 1. And now the thing I want to do is reindex this series. This is a thing that's by and large a huge hassle, and nobody likes doing it. And I'm going through this proof the technical way because I want you to have seen this early. You're going to have to be doing this on this upcoming exam, and it's a huge pain. And here's how I like thinking about it. Like, you can think about it the way you do with an integral by substitution. This way we write the standard way of indexing a sum is one way to do it. Another way to do it is to write that as an inequality. The values of k we're talking about are the values of k where k is between 1 and n. What I'm going to do now is I'm going to add 1 to all three sides of this inequality. K being between 1 and n is the exact same as saying that k plus 1 is between 2 and n plus 1, right? I feel comfortable making this switch because this inequality is definitely the exact same as this inequality, right? Now I'm going to switch letters. You probably wouldn't write this stuff step out if you're writing a paragraph explaining what's going on. I'm going to pick a new letter. I'm going to let u be k plus 1, because I'm thinking like this is a u substitution. K plus 1 going from 2 to n plus 1, negative 1 to the 1/2 to the k plus 1, well, where this is only a sentence about k plus 1, this is the exact same as saying that the sum from 2 less than or equal to u less than or equal to n plus 1, 1/2 to the u. And the letter u doesn't matter. This is the same as saying this will equal the sum from 2 less than or equal to k less than or equal to n plus 1, 1/2 to the k. There's a big difference between what we're doing here and what we're doing with an integral by substitution. If I'm doing an integral of, I don't know, e to the x over e to the x plus 1 dx, and I want to let u be e to the x plus 1. Ugh. So du is e to the x dx, and this turns into the integral of 1 over u du. You wouldn't be allowed to just say this equals the integral of 1 over x dx, right? The letter x in this context is not what we call a dummy variable. The letter x actually matters. Our end answer here is going to be some function of x, so the letter x has some meaning outside of the paragraph, and our answer cares about the letter x. In this context, the letter k is a dummy variable. We need it to not have any meaning outside of the sum. If it turns out that k was 3, then you're trying to talk about the sum from 3 equals 1 to n of 1/2 to the 3, which doesn't make any sense at all. So k is not only doesn't have a meaning, it can't have a meaning. If it did have a meaning, this whole expression doesn't make sense. This is what it means to be a dummy variable. This is, I don't know if this is the best analogy, but it's like when if you tell a joke about 3 guys who walk into a bar and the first one says to the second one that the something something something, if the joke gets too complicated, where I have to care about which guy is which, then we need to give those guys names. We say Sam and Joe walk into a bar, and Sam does this and Joe does that, and the words Sam and Joe don't mean anything, right? And it's kind of important that they don't mean anything. If I'm trying to explain a joke very well, where it's 2 guys walk into a bar, and I said, let's say the guys are Barack Obama and Keanu Reeves, those are bad choices of names, because now I'm not talking about 2 hypothetical guys anymore. Those names already have meaning outside the context of the joke, unless I'm telling a joke about Keanu Reeves and Barack Obama, it doesn't work, right? So that's what's going on here. In this expression, the letter k is a dummy variable where it doesn't have meaning, which is why when I do this substitution to the letter u and then switch back to the letter k, I'm allowed to do that in a way that I'm not allowed to do in an integral by substitution, at least if it's an indefinite integral by substitution. If there were little letters here, if I was an integral from 2 to 3, the integral from 2 to 3, 1 over u du, does equal the integral from 2 to 3, 1 over x dx. Because now these things are just numbers. The answer to that expression has no bearing on the letter x or u. The same way this thing turns out to be the number 1, doesn't care what k is. Okay, I feel like I've talked about this too much. I'm going to keep moving on. This thing reindexes to this. You will usually see people not write this step out, but when you're like learning for the first time, this is a really useful way to make sure you're doing it right. It's really counterintuitive. Like, the goal is to do this the long way enough times that you can look at this line. K goes from 1 to n, 1/2 to the k plus 1. You'd really like to be able to just rewrite that as this. 2 goes from k to n plus 1 of 1/2 to the k. I have a real hard time with this, like even still. Like these numbers went up and this number went down, and it feels like I should be going up to match it or something. To me, it's not obvious that when I add 1 to the bounds here, what I'm really doing is subtracting 1 from the k, and then I'm also subtracting 1 from the k here to match it. It's not easy. Like, it's legit confusing. It's reasonable to be confused, and it's reasonable to write out some extra lines to help you get through that. If you are absolutely lost, like the strongest thing you can do on a piece of scratch paper to check that you're re-indexing correctly is to just write out what is this with a ... This thing is, when k is 1, I get 1/2 to the 2. When k is 2, I get 1/2 to the 3. Plus ... The last term will be when k is n, 1/2 to the n plus 1. When I look at k equals 2, this becomes 1/2 to the... k is 2 is the first term, 2. The next term will be k is 3, 1/2 to the 3, ... The last term will be 1/2 to the n plus 1. This is the same as this, so these are the same series. Writing down what this is correctly is usually like way harder than checking that something you've written down is correct, which you just think about the first few terms in your head and check that they are coming out to be the same. Anyway, reindexing. This reindexing says now we have that I can rewrite Sn. So this thing and this thing look the same, but they have different bounds of integration. I can write Sn is, I'm going to peel off the first term of Sn, because this thing starts at 2. I want to make this expression and this expression even more comparable. Sn is 1/2 to the 1, plus the sum from k equals 2 to n, 1/2 to the k. I'm allowed to peel off one of the terms and now add up the rest of the terms. 1/2 Sn is, I want to peel off the last term of this. The sum from k equals 2 to n plus 1. Oh no, not n plus 1. I'm pulling off the last term. From 2 to n, 1/2 to the k, plus the last term. 1/2 to the n plus 1. So, Sn minus 1/2 Sn is going to be this minus this. Those things cancel. This is a way of canceling all those middle terms without using a ... is 1/2 minus 1/2 to the n plus 1. Thus, half Sn is 1/2 minus 1/2 to the n plus 1, and so Sn is 1 minus 1/2 to the n. This is a way of doing that without a ... is the point I was trying to make. This way is probably easier to understand, like showing the second term here cancels first term here, third term here cancels second term here. This is the good way to understand what's going on. This is the more mathematically correct way to do it that doesn't have the hand waving that a ... has. You're going to have to reindex series eventually. Okay, I'm going to stop talking about this slide. Let's move on. Let's do a general geometric series. Let's consider the sum from k equals 0 to infinity, a times r to the k. This is the general way of writing a geometric series. If you talked about a geometric function in some algebra class, it was c times a to the x. Our x is going to be k. The traditional way of writing it here is with a as the first term and r is the ratio, is what that r stands for. Here a was a growth factor. It's the same type of formula, but this is the way we do it for a geometric series. This is the standard form. Of a geometric series. What's a geometric series? A geometric series is one where I guess a geometric sequence is one where the ratio of consecutive terms is constant. So an plus 1 over an is always the same thing. This is the definition of geometric sequence. I'm avoiding defining what a geometric series is because a series is not actually a mathematical object. I'll say what I mean by that in a second. And this is a real confusing concept. Consider this. I'll multiply both sides by r. Sn will be the sum from k equals 0 to n, a times r to the k. And Rsn will be the sum from k equals 0 to n of a times r to the k plus 1 is the sum from k equals 1 to n plus 1, a times r to the k. Did I do that right? First term is a times r here. First term here is a times r. Last term here is a times r to the n plus 1. Last term here is a times r to the n plus 1. Looks good. Looks like we haven't messed this up. And so Sn minus Rsn is going to be this minus this, sum from k equals 0 to n, a times r to the k, minus the sum from k equals 1 to n plus 1, a times r to the k, equals, everything cancels except for the 0th term here, a times r to the 0, minus everything cancels except the last term here, a times r to the n plus 1. This equals 1 minus r Sn. So Sn is a minus a r to the n plus 1 over 1 minus r. Maybe you factor out the a. And I can stare at this sequence and think about when does it converge. And you conclude that if absolute value of r is less than 1, those are the times when I have a small number, I'm raising it to a big power, it gets close to 0, then Sn converges to a times 1 minus 0 over 1 minus r, is a over 1 minus r. If the absolute value of r is bigger than or equal to 0, then it doesn't converge at all. It is bigger than or equal to 1. 1. Oh, actually, this works if r is bigger than 1, or r is less than or equal to negative 1. Yeah, if r equals 1, it also doesn't converge. But this expression doesn't make any sense when r is 1. If I plugged in r equals 1, the sequence 1 to the n does converge. It'll converge to 0. And this expression will give you 0 on top, but it's also giving you 0 on bottom. So you're getting some weird undefined thing. The thing is, if r equals 1, I wasn't allowed to divide both sides by 1 minus r. If r equals 1, this whole expression doesn't work as a trick. But when r is 1, then the sum from k equals 1 to n of a times r to the k is going to be the sum from k equals 1 to n of a. What do you get if you add together n copies of the letter a? You get n times a, which doesn't converge. I guess unless a is 0. Cool. Cool. So here's what we can conclude. Oh. Yeah, this thing, why does this not converge if r is bigger than 1? If r is bigger than 1, I'm taking a big number and raising it to higher and higher powers. Doesn't converge. 1 minus that will go to 1 minus infinity, divided by a constant, goes to negative infinity, undefined. I guess it'll go to positive infinity because we're dividing by a negative. Doesn't matter. I guess maybe a is negative. Either way, it doesn't converge. If r is less than or less than negative 1, same deal. Now it's alternating between big positive number and big negative number. It doesn't converge. If r equals negative 1, then this is negative 1 to the n. I have 1 minus 1, 1 minus negative 1, 1 minus 1, 1 minus negative 1. That sequence is 0, 2, 0, 2, 0, 2. That sequence, you do some epsilon stuff, doesn't converge. It's not getting closer and closer to something, unless a is 0. If a is 0, this thing always converges and life is easy. Conclude. If a is not 0, then the series, the geometric series, sum n equals 0 to infinity a times r to the n converges to a over 1 minus r when the absolute value of r is less than 1, and diverges when absolute value of r is greater than or equal to 1. And if a equals 0, it converges trivially. If a is 0, then you're trying to add up infinitely many zeros. That's pretty easy. Infinitely many zeros will add up to 0. Most textbooks will give you this formula. I think this formula is not the useful way to do it because it sort of relies on the thing starting at n equals 0. I usually remember it in my head as the sum of a geometric series is first term over 1 minus r. So for example, if you hand me the sum from k equals 3 to infinity of 1/2 to the 2k plus 1, maybe not use 1/2, let's make it 1/3. This is gross. I got all sorts of junk going on. One, this turns out to be geometric. If I really want to force it to look geometric, I can rewrite it as the sum from k equals 3 to infinity of 1/3 to the 1 times 1/3 to the 2k. That's the sum from k equals 3 to infinity of 1/3 times 1/3. I'm going to insert some parentheses here. That's 1/9 to the k. Even if I don't want to do that, I can just think about the first few terms and confirm that they're doing what they're supposed to do. The first term will be when k is 3 is 1/3 to the 7. The next term will be when k is 4, it's 1/3 to the 2 times 4 plus 1 is 9. The next term will be 1/3 to the 3 times 3 plus 1 is 11. 1/3 to the 13. What am I multiplying to get from one term to the next? I'm multiplying by 1/3 squared. Multiply by 1/3 squared. Multiply by 1/3 squared. Like, just writing a couple terms is enough to check that we are multiplying by the same thing when we move from term to term to term. There's a constant factor that you shift by. Does the series converge? 1/3 squared is 1/9. 1/9 is between -1 and 1. So yes, it converges. Saying that 1/9 is between -1 and 1 is the same as saying the absolute value of 1/9 is less than 1. They usually write it with this absolute value notation as a slightly slicker way of describing this inequality. It's traditional to use that weird, slightly slicker way of doing it. Yes, it converges. What does it converge to? This thing doesn't start with k equals 0. To make this formula work, you have to re-index it so that k is 0. That's a hassle. I recommend remembering its first term over 1 minus r. It converges to, what's the first term of the series? The first term of the series is 1/3 to the 7. If I hadn't written this out, I'm staring at that and plugging k equals 3 into that. Over 1 minus, I need to know the ratio is 1/9. I know that, however. What's 1 over 3 to the 7? I guess I don't care what 3 to the 7 is. Times 1 over 1 minus a ninth is 8/9. That's 9 over 8. Times 1 over 3 to the 7. 2 of those 3's will cancel. I get 1 over 8 times 3 to the 5th. I can find out that number. I don't care what that number is. This is what that series converges to. The sum from k equals 3 to infinity of 1/3 to the 2k plus 1 turns out to be 1 over 8 times 3 to the 5th. I'll do it. What's 3 to the 5th? Times 8. It's 1944. 1 over 1944. We evaluated that geometric series. If the ratio had been 9/8, then that's a number that's bigger than 1. We would say the thing doesn't converge. And we could use this formula, but the formula's not telling me anything because the thing just doesn't converge to that. I said this weird sentence a second ago, that a geometric series is not a mathematical object. What did I mean by that? In math, we have some of these capital D definitions, where this is the name of a thing, and in math you want to be able to check if something has this property or it doesn't have this property. Like, is the structure you're talking about a sequence? The property of being a sequence is well defined, right? There are things that are sequences and there are things that are not sequences, and the difference should be clear. The difference is not clear for a series. Why? If you want to say that this is a geometric series, well, this thing equals 1 over 1944. If geometric series was a mathematical definition, then it would be preserved under equals. This being a geometric series would tell you that this is a geometric series. And immediately every real number is a geometric series. Like, we haven't done it, but you can rig up an example. I guess we saw one where it converges to 1. So multiply that by your constant c, and now you have a geometric series that converges to c. So this idea of being a geometric series is not actually a mathematical term. Mathematical terms respect equals. This concept is a learning tool, but is not a mathematical definition, if that makes sense. Like, the property of being a geometric series is not preserved under equals, so we don't, it is a bad word in that sense. Maybe bad is not the right, I don't know, there's something lacking in that definition, and I try to avoid making definitions and theorems and mathematical statements that depend on whether something is a geometric series. The right way to talk about it is to say that the sequence 1/3 to the 2k plus 1 is a geometric sequence. The property of being a geometric sequence can be made well-defined. We know what a sequence is. If a sequence equals something, that thing is a sequence. We don't say that a sequence equals its limit the way we say that a series equals the thing that it converges to. Okay, so that's a geometric series. The big question we're going to be answering, so we've defined what an infinite series is. Our main goal, if exam 1 was about, I'm going to give you an integral and you're going to tell me whether it converges, or what it converges to, no, I'm going to give you an integral and you're going to do the integral. That's what you did on exam 1. In exam 2, I'm going to hand you an infinite series and you're going to tell me whether it converges. You would think that the answer is going to be tell me what it converges to, like we just did for a geometric series. It turns out most of the time evaluating an infinite series is just a way harder question. It's bigger than the topic we're going to talk about now in Cal 2. The main question is that given an infinite series, does it converge? For exam 1, like most of the points on the test were here's an integral, do it. For exam 2, I don't know if it's going to end up being most of the points, but lots of the questions will be here is an infinite series, tell me if it converges. Give me an explanation for how you know it converges or doesn't converge. So we're going to end up with a bunch of facts that have names. They're going to be called tests usually. And they're going to be ways to look at a series and tell whether it converges or not. The one we just did was geometric series. That's not really a test, that's more an example. When something is a geometric series, that's the rare occasion that you can figure out what it adds to. Most series are not geometric. Let's state the first test. I'm wandering too much. The first test is called the divergence test. Let's do a little sketch of what we can confirm from the divergence test. If suppose the sum from k equals 1 to infinity ak converges. If it converges, then when n is large, for all large n, we have the sum from k equals 1 to n of ak is going to be very close to L. This is what it means for the series to converge, is that the sequence of partial sums converges. So this partial sum, the nth partial sum, if n is very big, will be very, very close to L. I could make this more specific, say that the difference between this and L is less than epsilon. But also, the sum from k equals 1 to n plus 1 of ak is also very close to L, because that's also a sum of lots of the terms. This means the difference between them, the sum of the first n plus 1 terms, minus the sum of the first n terms, is about L minus L is about 0. I could be more specific and technical than I'm getting. I could say you're within epsilon of L and you're within epsilon of L. So if I subtract two numbers that are so close to L they're within an epsilon, then they'll be at most 2 epsilon away from each other, which will be very close to 0 because epsilon started out as a very small number. But what do I get when I subtract the first n plus 1 terms minus the first n terms? These series are all the same. Like, all the terms cancel except for the last term of this one is an plus 1. An plus 1 is about 0. We get that the n plus 1th term is very close to 0. This makes sense. If you want to add up infinitely many numbers, the numbers better be pretty small. How small? Smaller and smaller. Like, if you have infinitely many numbers that are bigger than 0.0001, then when I try to add them all up, they're going to be bigger than 0.001 times infinity, which is still infinite. They need to eventually be smaller than any gap. The terms are close to zero, and in particular, they're closer and closer to zero. That's what the divergence test says. The divergence test, you can sort of phrase it two ways, is that if the sum from k equals, let's say some starting term. I don't actually... Okay, so let's get used to this. I'm going to state this about the sum from k equals 1 to infinity of ak. If you have a series that doesn't start at 1, if your series starts at 20, you know that the sum of the first 19 terms converges. It's the 20 past it's the part at the end. Does that add up to infinity or not, is the question we still have. So I'm going to state it for k equals 1 to infinity. That's my default way of talking about a series. But the question of whether the series converges doesn't care about how many terms it starts with. What's the number of the first term? That doesn't matter to this. You can use this test even if k starts not at 1. If this sum converges, then the limit of k goes to infinity ak must be 0. That's what we just concluded a second ago. If you want to add up infinitely many numbers, then numbers better get smaller and smaller. Smaller and smaller is maybe not the right word. That implies that it's strictly decreasing, getting closer and closer to 0. It doesn't need to be closer and closer to 0. It just needs to have a limit of 0. You can come up with sequences whose limit is 0 who aren't getting smaller every step. Okay, don't dwell on that, Andy. What we're usually going to use, though, is the contrapositive. What's the contrapositive? Most mathematical statements are of the form, if something is true, then something else is true. The contrapositive is, if B is wrong, then the original is wrong. Every statement is logically equivalent to its contrapositive. Saying this is the same as saying that. Like turning the sentence, like clearly, if you know that every convergent sequence has that the limit is 0, you know that if the limit is not 0, there are two ways to not be 0 we should keep in mind. Either because it doesn't converge, either the limit doesn't exist, or the limit is some non-zero number. Either version works for this. Then the sum from k equals 1 to infinity, ak, doesn't converge. It diverges. Diverge is the word for not converge. We say a sequence or series diverges exactly when it does not converge. And going to infinity counts as diverging. Going to infinity doesn't count as converging. That's not a limit. Going to infinity is not the only way you can diverge. You can go all over the place and never get closer to something. Those both count as divergence. Every statement is equivalent to its contrapositive. Suppose we know this fact, which we do now. If a series converges, then the sequence of its terms is 0. Well, that means that if this wasn't true, that couldn't have been true, right? So we know that this statement causes this one. If you believe the first one, you should believe the second one. The second one says, if the limit is not 0, then the series could not have converged. But notice there's a symmetry to this. Suppose now that I know this fact, if the limit is not 0, then the series must diverge. Well, that tells me that if the series didn't diverge, the limit couldn't have been not 0, which is equivalent to saying if the series converged, then the limit was 0. These two statements are logically equivalent. If you believe one, then you must believe the other. If one is true, the other is true. If one is false, the other is false. This is what logically equivalent means. They have the same truth value no matter what. And in this case, their truth value is true because this is a theorem. That's the divergence test. The divergence test is a very weak test. The divergence test is like a bare minimum prerequisite if you want to have any chance of your series converging. If I hand you a series and the terms don't get close to 0, your response is, you're not even trying. There's no way that converges. You're not even doing the bare minimum. It's worth noting that the geometric series, the ones that don't converge, they really don't converge. They fail the divergence test. If the terms are bigger than 1, then a times r to the n is getting bigger and bigger and bigger. If r equals 1, then it's not getting bigger, but it's not getting smaller. It's not getting close to 0. If r is negative 1, it's not getting bigger or smaller, but it's flopping around between positive and negative, doesn't get close to 0. If r is a big negative number, then it's both getting bigger and bigger and switching between positive and negative. All of the versions where the r value is not got absolute value less than 1 fail the divergence test. Geometric series are sort of a very weak type of series because when they converge very fast and easy. And when they diverge, they have no chance of converging in the first place. They're sort of extremes on both ends. And the fact that when r passes from less than 1 to bigger than 1, it flops in a really strong way. I don't know where I was going for the end of that sentence. The key thing about the divergence test, it feels like I said two things, but I really only said one thing. These two statements are the same thing. The divergence test can show you that the series diverges. Notice that the converse is not the case. I'm going to write this in red to make it warning. Warning. Just because the limit of a sequence is 0 doesn't mean that the sum of the terms converges. And the divergence test does not tell you that. The divergence test is called the divergence test because it can only give you divergence. It will never tell you that something converges. Yeah, every year someone tries to do that on the test, and that's not what the divergence test does or can do. I can give you an example of this. This is the standard example of the first tricky series. This is the harmonic series. It's a special series that gets a name, the harmonic series. I'm not totally clear on why it's called a harmonic series. I think it might have to do with the lengths of the strings on a stringed instrument. Is the harmony part of it? I don't know. If you learn it, let me know. The harmonic series is the sum from n equals 1 to infinity of 1 over n. This is 1 plus a half plus a third. Nope, the 3 goes on bottom in a third. A third plus a fourth plus dot dot dot. Note that the divergence test tells us nothing here. The terms do go to 0. If the terms didn't go to 0, I would know it diverges, but they do go to 0 here. The terms are getting smaller and smaller. So maybe that should cause us to expect that the series converges. Well, the thing I just wrote in red says, hey, no, don't learn that. That is not a thing to expect. The terms getting small tells you nothing. The terms getting small is just a bare minimum that you must satisfy to have a chance of converging. And the harmonic series is the first counterexample that the terms getting smaller is not enough. Let's show that the harmonic series diverges. Theorem. The sum from n equals 1 to infinity of 1 over n diverges. This is plus infinity. It doesn't converge to anything. It gets bigger and bigger without bound. Let me show you why. Throw away the first term. Ignore that. Look at this term that's a half. Look at the next two terms. They are a third plus a fourth. How big is a third plus a fourth? The smaller of those numbers is a fourth, right? So this is bigger than a fourth plus a fourth. This is bigger than a half. This thing is a half. Let's go from a fifth out through an eighth. The smallest of these numbers is the one with the biggest denominator is 1/8. This is bigger than 1/8 plus 1/8 plus 1/8 plus 1/8 is a half. If I go out from 1/9 to 1/16, this is 8 numbers that are all bigger than a 16th. 8/16 is a half. So, for any, let's try phrasing it this way, for any m, there is some n, so that the sum of the first n terms is bigger than 1 plus a half plus a half plus a half plus dot 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 plus a half, where we have m times. No matter how many 1/2s you want, you can take enough terms of the harmonic series, and you'll probably need a lot. The number of terms you need is doubling at every step. So this is 1 term, 2 terms, 4 terms, 8 terms. If you want m of them, you'll need 1 plus 2 plus 4 plus dot 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 plus 2 to the m plus 1 more for the first term that doesn't fit the pattern that we ignore, is bigger than 1 plus a half of m, which goes to plus infinity. The series can't converge if it's bigger than something that goes to infinity, and it's positive. So the series diverges. The harmonic series is an example of a series where even though the terms go to 0, the series diverges. If we were in a classroom, I guess if we were in a classroom and there's a fun activity you can do in a calculus class to do with textbooks. The fact that the harmonic series diverges makes this weird thing true. Suppose I have a table, and there's the edge of the table, and I have a calculus textbook. I can put the calculus textbook so that it sticks out over the edge of the table, right? How much of the calculus book is allowed to stick out over the edge? Anything less than a half, right? But I can get as close to a half as I want. I can say that there's basically a half of the calculus textbook sticking out there. Well, let's say I didn't stick that on the edge of the table. I stuck that on the edge of a calculus book that is still sitting on a table. How far can I stick the lower calculus book out over the edge of the table? It turns out, if I've got it right, that the answer is a third. Like if you think about, this one can stick out as much as a half of the one over it before it falls. If I look at these two with a half and a third here, now we've got it so that the center of gravity of them is right at the edge of the table. Have I got this right? A half and a third? Oh, it needs to be here, like a 3/4. Oh, I messed it up. This is what I get for not doing this, running these numbers before class. This will be a 1/4. Is the place where, like, the first book is already halfway out over the book below it, right? Man, I'm messing this up. The punchline, and I'm not doing a good job of getting to the punchline, is that the amounts that you can stack books out and stick their tips over the edge turns out to be a harmonic series. It's off by some constant. Oh yeah, this is a half, this is half of a half, the next one will be a third of a half, will be 1/6, is the place where the next center of gravity matches up in the next one. So that if you just want to use a stack of enough books, how far can you stick them out over the table? You can stick them out as far as you want. There's no limit to how far a stack of textbooks can reach out over the edge of a table, because the harmonic series diverges. It'll go out forever. You can build a bridge like that. I don't recommend building a bridge like that. I'm not going to drive on that bridge. And it's fun if you have a room full of 30 students who all brought a calculus textbook, and you can show them that, whoa, look, it's sticking out over the edge. I suppose there's some points we should say. These are some obvious facts that are not deep or anything, but I'm going to stay with them. Note, series are linear. The sum from n equals 1, let's write it k equals 1 to n of c times ak. You can factor out the c. And the sum from k equals 1 to infinity of c times ak equals c times the sum k equals 1 to infinity ak, if the right-hand side converges. You'll be tempted to say if the left-hand side converges, then the right-hand side should converge also. It doesn't work in that direction because maybe c was 0. If c is 0, the left-hand side definitely converges no matter what was going on the right. You might want to say, well, 0 times something that diverges must converge. Well, that's not the case. 0 times infinity isn't automatically 0. And diverging doesn't just mean infinity. Also, if the sum from k equals 1 to n of ak plus bk is the sum from k equals 1 to n of ak plus the sum from k equals 1 to n of bk. You want to add up a bunch of numbers pairwise. You might as well just add up these guys and add up those guys, and you will get the same thing. And the thing I want to say is the sum from k equals 1 to infinity of ak plus bk should be the sum from k equals 1 to infinity of ak plus the sum from k equals 1 to infinity of bk. But again, there's an asterisk on this, where do these things actually converge? I can come up with this not converging and this not converging, but this converging. The best statement you can get, I think, is this statement is true if any two of the three series converge. If two of them converge, then the other one must converge, and this formula works. If only one of these converges, like I can do the sum from k equals 1 to infinity of -1 plus 1, that converges because you're adding up infinitely many zeros. This does not equal the sum from k equals 1 to infinity of -1 plus the sum from k equals 1 to infinity of 1. You'll be tempted to say that adding up infinitely many negative ones gives you negative infinity. Adding up infinitely many ones gives you plus infinity. And it's tempting to say, well, that's what's going on. That's why this is allowed to exist. But that's too much whitewashing. That doesn't get at what's going on. You're not allowed to say negative infinity plus infinity is 0. In particular, because I can pull off one of those terms. Now I have 1 plus infinity. And it doesn't add up to 1. So, right. This is sort of the first hint that we've got that there's something suspicious going on when you try to add up infinitely many numbers. When you're adding up finitely many numbers, we know that the order you add them up in doesn't matter. And that feels like a fundamental property of addition, that rearranging the order of the things you add up doesn't change what the sum is. When you start adding up infinitely many things, that becomes suspect. That is not automatically obviously true. And in fact, we will see in a week or so, a situation where that is not true. And it's awful. But that's it for today. I'm going to stop lecturing for now. We haven't seen that much of the homework you can do. I still have the homework up. There it is. You should be able to do 86, 87, 88. The things after 88 you need some more work on. Like we need some more tests. But you can look at those problems to see that's where we're headed. Here's a series, and I'm asking you, does it converge? Is what we're going to be doing eventually. Rock on, I'll see you tomorrow. Hopefully tomorrow we'll get through enough that you can do at least some of the homework over the weekend, because you want to get started on this sooner rather than later. See ya.